array of telescopes, both on the ground and in orbit, we found 992 exoplanets. And we can now begin to characterise those planets, to search for signs of life encoded in the faint light from these distant worlds. So far, one of the best candidates for life orbits around one of the stars in this constellation, in the constellation of Lyra. It's a planet called Pt.62e, after the recently retired Kepler telescope that first identified it. It seems to be just the right size and mass to make it a rocky planet, and in just the right orbit to give it a chance of possessing liquid water on its surface. But remarkably, we can do better than simply estimating what these planets are made of. See, we're on the verge of being able to look directly into the atmospheres of these planets and search for the telltale fingerprints of life. And I'm going to ask Charles Dance to come down and help me show you how.
I've got a coat, have I?
Yeah, I think it's fireproof.
Thank you very much. Thank you.
So, what we're going to do here...
You just want me to clean this trolley, don't you?
Yeah, just give you a mop.
Yeah.
What we're going to do is we're going to demonstrate the technique that astronomers use to identify the presence of chemicals in the atmosphere. You can stand wherever you want. It's not going to help you at all. So what I'm going to ask you to do is we've got a selection of 4 chemical elements dissolved in these solutions, and I want you to spray them through the Bunsen flame.
Which direction would you like me to spray them?
I think actually probably sort of just upwards and
really?
outwards.
Sure.
There, yeah.
In any particular order?
No. Just let's see what happens. So you can see, apart from this one, they're all colourless liquids, but they've got chemical elements dissolved in solution.
All right.
So let's have a go at that. We could dim the lights a bit, actually, perhaps. Could we? Go on, let's spray that one through. Let's see what that does.
OK.
There it goes.
Can I do that again?
Go again. Beautiful green colour, bright green colour. So now let's try that one.
Same thing?
Yeah.
Oh, I like that.
A bright red.
This takes me back.
And to school chemistry lesson.
No, to early psychedelic rock concert.
I quite like that one, actually. Oh,
What
where's
if
the
we
red?
do 2 together?
Oh, go on, let's do it. Let's go for it.
We do 3 together.
Thank you very much. Now, the reason that those chemical elements behaved in different ways is down to the structure of the elements themselves. See, what happens when you burn that element, when you heat it up, is the electrons jump around between different orbits around the atomic nucleus and then fall back down again and emit light. And so what we're seeing there is the structure of the atoms themselves that make up the chemical elements. Each element will have a different signature of light that it emits when heated because it has a different configuration of electrons around the nucleus. Now, as well as emitting light when heated, elements also absorb light of exactly the same colour if they're present in the atmosphere of a star.